This time we're going to learn about rolling without slipping. Rolling is a combination of a motion. You can see in this diagram that a point on a rim traces out a semicircle motion, also known as a cycloid, and there's also a translation path of a center wheel. We know that the displacement equals velocity times time. But what is also interesting is in one rotation time, the center of mass travels the circumference of the circle. There we have the equation velocity times time equals 2 pi radius. To solve for the velocity of mass, you would reorganize the equation and find v equals 2 pi r over the period. But also note that 2 pi over period equals the angular velocity. Now we can reorganize this equation to have velocity of center mass equals r times angular velocity. However, if we, in order to find the acceleration of center of mass, we would take the derivative of this equation. And the derivative of this equation is r times alpha. As I stated before, rolling is a combination of motion. So translation plus rotation equals rolling. And this diagram shows this part is the translation of center of mass, where every point is traveling in a same velocity. And in this point, it shows that each point is rotating at angular velocity times r. What is important to know in rolling without slipping is that friction must be present, and friction is static. That is why rolling without slipping occurs. And in order to use this equation, there's two conditions where it has to be fixed in an inertial reference frame, and it has to be also fixed in direction but passes through the center of mass of the body.
Okay, so today we're going to be looking at an AP problem. This is from 1997 Mechanics 3, and we're going to be looking at a cylinder with mass m and radius r and rotational inertia 1/2 mr squared rolling down an inclined plane without slipping. So first I'm going to draw this, and this has height h, angle theta, and we have our ball here with radius r and mass m. And so part A is asking to find the translational speed of the cylinder when it reaches the bottom of the inclined plane. So for part A, we have to think about energy for this. So before, we have, so the potential energy is going to be equal to mgh. Well, this here, we're going to set as our potential energy is equal to 0 line. So before we have mgh, that's equal to u, and kinetic translational energy, we have none. And now we also have, we have no kinetic rotational energy. Now after, we have no, because once the cylinder reaches the bottom, there's no potential energy, so we're left with translational and rotational kinetic energy. So this is going to be equal 1/2 mv squared. That's that. And then the rotational is equal to 1/2 I omega squared. Now, for this case, we know that when something is rolling without slipping, we can use the rolling constraint, where omega r is equal to v. That's going to come in handy later. So first, we're going to start by writing energy initial is equal to energy final. So energy before is equal to mgh. Energy after is equal to 1/2 mv squared plus 1/2 I omega squared. And now we have I, which they gave as 1/2 mr squared, and omega is equal to v over r. So we can substitute that in. We get mgh is equal to 1/2 mv squared plus 1/2 mr squared times, now it's omega squared, so it's going to be v squared over r squared, and these cancel out. And we also can cancel out the masses on everything. So we're left with gh is equal to 1/2 v squared plus 1/4 v squared. Now when we add that, we get gh is equal to 3/4 v squared. And now when we solve for v squared, we get v is equal to the square root of 4/3 gh. And that's part A. Now part B is saying, on the figure below, draw and label the forces acting on the cylinder as it rolls down the inclined plane. So I'm just going to draw a line here that's going to represent, let me draw a little more accurate. So this is going to represent our inclined plane, and we're going to draw our circle here, our cylinder. And so force of gravity is coming from the center, and then there's a normal force perpendicular to the plane, or the inclined plane. And then we also have our force of static friction. And it's static because, remember, this cylinder is rolling without slipping. And that is part B. And so for part C, it's saying, show that the acceleration of the center of mass of the cylinder while it is rolling down the inclined plane is 2/3 g sine theta. So we're going to be looking for 2/3 g sine theta. I'll just bubble that. Okay, so I'm going to erase what I had before for part A here. So we don't need that anymore. And I'm also I'll keep that. Let's just write down that v is equal to the square root of 4/3 gh. Okay, so for part C, we're going to want to use the equation vf squared is equal to v naught squared plus 2ad. And d, in this case, we're going to label as this. So first we'll find d. So d, so sine theta is going to be equal to h over d. So d is equal to h over sine theta. And now in this case, we know that this cylinder is initially at rest. So v naught is equal to 0. So we're left with this. And now we're solving for acceleration. So A is equal to vf squared over 2d. And now we can plug in our velocity final, which we found earlier, and d. So we get A is equal to, now we're squaring a square root, so we get 4/3 gh over 2 times h sine theta. Now we cancel out the h's. This comes 2. Now sine theta goes to the top, and we're left with A is equal to 2/3 mg sine theta. Okay, and that's part C. I'm also gonna let me make some room. So we know that A is equal to 2/3 g sine theta. And now, part D asks, determine the minimum coefficient of friction between the cylinder and the inclined plane that is required for the cylinder to roll without slipping. So I'm just going to quickly erase this. And so for this part, we're going to want to use a sigma f statement because we're looking for mu, or the coefficient of friction. So we're going to start with sigma f. We'll do the y direction. We know that it's not going up or down, so acceleration is 0. So then we're left with Fn minus Fg. Oh, and I should give a sign convention as well, which we're going to say is this, just to make the problem easier. So we know that Fn is going to be equal to Fg, but in this case it's going to be Fg cosine theta. So this is going to be mg cosine theta. And now I'm going to do sigma f in the x direction. Sigma f x. And this is equal to ma, and this is accelerating downwards. And now we have mg sine theta minus fs is equal to ma. And now we know that fs is equal to mu fn, and so we can plug this right in there, and we get fs is equal to mu mg cosine theta. Now we plug this in, we get mg sine theta minus mu mg cosine theta is equal to m, and a, as we found earlier, is 2/3 g sine theta. So 2/3 g sine theta. Now we can cancel out mg from every term, so we're left with, and then I'm going to add the mu cosine theta to this side and subtract the 2/3 sine theta to the other side. So we're left with sine theta minus 2/3 sine theta is equal to mu cosine theta. And now we get 1/3 sine theta is equal to mu cosine theta. Now solving for mu, we get 1/3 tan theta. And that is our final answer for D.
We talk about rolling with slipping, which is a different problem from rolling without slipping because you do not have the rolling assumption. Now, with rolling without slipping, you have the assumption that the velocity of the object is equal to omega, the angular velocity of the object, times the radius, which means that the graph of something would look like this. The velocity is equal to omega times r. Now, with rolling with slipping, that's not the case because in the beginning, it is not rolling as fast or as slowly as it is actually moving. So you would have, let's say, velocity that starts up here and rotational velocity omega start down here. And velocity will gradually decrease while the rotational velocity will gradually increase until they meet at this point, and then it continues on to roll without slipping. So the first thing that we're going to do with a rolling with slipping problem is to draw a force diagram. Now, we have a hollow sphere that's going to be this circle right here, and we know that there's going to be a Fg with an equal and opposite Fn. Whoops. And we're also going to have a kinetic frictional force, Fk. Now, one important thing about rolling with slipping problems is that you have to pick the right sign notation. So we're going to have up and to the right be the translational positive, and also clockwise be the rotational positive. Because when it rotates clockwise, it goes towards the positive translational velocity. Okay, so after doing that, we can start doing our sigma f statements. Now, with this problem, you have to break it up into two parts, the translational part and the rotational part. So we have it here. In the translational part, we know that there is a frictional force. So we can say the sum of fx is equal to whatever the normal force is times mu k. And we know that that is actually in the negative direction. So we also know that the sum of Fy is equal to 0, which is equal to Fg minus Fn, which means that the normal force is basically mg. So now we know that the translational velocity is going to be v of t is equal to the original velocity minus this acceleration, after dividing it by mass, times t. So we know that Fn is mg, which means that it's mg mu k over m times t, which simplifies to v naught minus g mu k t. Now we're going to work on the rotational part of the problem. We know that the sum of the torque is equal to whatever that frictional force was times the radius from the center of the hollow sphere. So we know that it is equal to times r, which is also equal to the same as this part, mg mu k times r. So then we can figure out the velocity with respect to t, which is equal to the original velocity, which is actually 0, plus whatever the angular acceleration is times the time. Now, angular acceleration is the net torque divided by the moment of inertia. And you have mg mu naught mu k times r over the moment of inertia of a hollow sphere, which is actually 2/3 mr squared. Now, that will probably be given to you on a formula sheet or something. That times t. So then we can simplify this as well. This is equal to 3/2 g mu k t all over r. Now we can actually combine these two together, because we know at some point t, the velocity will equal to the angular velocity times r. So we say that v naught minus g mu k t is actually equal to, at some point t, equal to 3/2 g mu k t over r times r. Now the r's cancel out, we move that around. V naught is equal to 5/2 g mu k t. We're solving for t, which means that we move this down here. We get v naught, 2/5 v naught over g mu k is equal to t. And now we found t at this point where the rolling with slipping problem becomes a rolling without slipping problem.
Here we have a billiard ball with mass m and radius r. It's initially struck with a velocity v naught across a table with coefficient of friction mu k. Eventually, the translational motion of the billiard ball turns into rolling without slipping. So first, let's find the change in velocity as a function of time. So let's draw a free body diagram. We have the force of gravity. We also have the normal force. And we also have the force of kinetic friction. So our sigma f statement for the y direction is equal to ma. And also we have to draw a sign convention here. And what's important to have a sign convention where when velocity is positive, the angular velocity is also positive. So if it's moving to the right, let's make up and to the right is positive, and it's going to be spinning this way. So let's make clockwise positive. Sigma F equals ma equals 0 because the net force in the y direction cancels out, and it's equal to Fn minus Fg. Therefore, Fn equals Fg equals mg. So in the x direction, f of x equals ma equals f of k. What does f of k equal? So we know mu k is equal to f of k over f of n. So f of k equals mu k times f of n equals ma. So the acceleration is equal to mu k mg over m, and the m's cancel out. So we know that velocity equals v naught plus a of t. So v is equal to v naught plus mu k g times t. Next, let's make a sigma tau statement. So sigma tau is equal to I alpha equals fk times r. And fk is equal to mu k mg. So sigma tau equals mu k mgr. So you know I equals 2/5 mr squared. So alpha ends up being mu k g over r times 5/2. So similarly, what we did for linear velocity, we can do for angular velocity. So we know that omega equals omega naught plus alpha t, but omega naught is 0. And alpha is 5/2 mu kg over r, so this ends up being 5/2 mu kgt over r. So now we have our function for linear velocity and for angular velocity. And at some point, the billiard ball rolls without slipping.